Hello students, this video lecture will cover section 4.6, the mean value theorem. So first we have to recognize that the mean value theorem is a very important theorem in calculus. In fact, many of the theorems that we've already stated in this course rely on the mean value theorem in order to hold true. And the theorem itself appears in many practical applications, one of which we'll look at involving meteorology. But first we'll start with a preliminary result proved in 1691 known as Rolle's theorem. Rolle's theorem says that if you have a continuous function on a closed interval and it's differentiable on the open interval, and the two endpoints of the function have the same value, in other words, f of a equals f of b, then there must exist at least one point inside the interval such that the derivative of that point is 0. So in this case we can see we have f of a equal to f of b, and at some point on this interval, at least one point, there has to be a spot where the derivative of this function is 0. And you can see in this case we've arrived at the local maximum, and in this case c has the derivative of 0. The proof of this theorem is somewhat important to understand. It says the function f satisfies the conditions of theorem 4.1, the extreme value theorem, which we went over already, and it attains its absolute maximum and minimum values somewhere on the closed interval AB. Now those values are attained somewhere, either at an endpoint or at an interior point on C. So if we take a function that attains both its absolute maximum and minimum values at the endpoints, because f of a equals f of b, then the maximum and minimum values are equal, so the function has to be a constant function, and so the derivative of the function is 0 for every point inside the open interval. That's kind of the boring case, I say. If we assume that at least one of the absolute extremes of f does not occur at an endpoint, then the function has to have an absolute extreme value at an interior point of the interval itself. Therefore, that function has to have either a local maximum or a local minimum at some point C in AB. Now, given the fact that the function is differentiable, we know that Theorem 4.2 tells us that a local extreme, the derivative is 0. Therefore, the derivative is 0 for at least one point, C of AB, and again the conclusion will hold true. So why does Rolle's theorem require continuity? Well, in the event that the function is not continuous, then we could have a situation where it's differentiable everywhere except at this point where the function is non-continuous. And because the function is non-continuous, what we end up with is a derivative that can be attained at any point on the open interval from A to this location here, and it's differentiable from here to this point B. But in this case, there's going to be no horizontal tangent line, and that's due to this discontinuity. We could actually flip this function across the x-axis and end up with the same situation. And continuity is not the only requirement here. We also have to have differentiability. So given some point on the interval where the function's not differentiable, we end up with the possibility again of not being able to find a horizontal tangent line. Example 1 asks us to verify Rolle's theorem. It says find an interval on which Rolle's theorem applies to x to the third minus 7x squared plus 10x. And then find all the points on the interval at which f prime of c equals 0. Now first we need to consider the two restrictions. We need to consider whether or not the function is continuous and differentiable. But here we're dealing with a polynomial, so that's not an issue at all. So at first we need to find some interval where the two y-coordinates or the two values of the function are exactly the same. Now one possible interval is the interval from 0 to 5. Because the function can be factored as x times x minus 2 times x minus 5, the interval 0 to 5 seems to make sense. We can make x 0 and the function is 0, or we can make x 5 and the function is still going to be 0. So here we have the value of the function 0 and the value of the function here is 0. So in this case we can take the derivative fairly easily. We get the derivative is 3x squared minus 14x plus 10, and we set that function equal to 0. And since this is a quadratic, we can use the quadratic formula to find the roots. We have 7 plus or minus the square root of 19 over 3. And you can see at those points, around 0.88 and around 3.79, we have a tangent line that is horizontal. So that brings us to the mean value theorem. So the mean value theorem is most easily taught by using a picture. So here we have a function that's differentiable on the open interval AB and a secant line that passes from one endpoint to the other. Its slope is the average rate of change of the function over the closed interval AB. We talked about that in previous lessons. The mean value theorem states that there must be some point C at which the slope of the tangent line at C is equal to the slope of the secant line. Basically, we have to be able to find some point on the graph where the tangent line and the secant line are parallel. So here we can see by moving C between A and B, we can eventually find a point at which we believe our tangent line and secant line are parallel. And there may be multiple points. You can see as we draw C along again, closer to B, there may be more than one point where the tangent line is parallel to the secant line. Remember, the mean value theorem doesn't tell us how many points, it just tells us that there has to be at least one. So here we have the mean value theorem. If a function is continuous on a closed interval AB and differentiable on that open interval, then there must be at least one point C inside the interval such that the slope of the tangent line is equal to the slope of the secant line. So you can see here it's given formulaically. On the left-hand side, we have the slope of the secant line, and on the right-hand side, we have the slope of the tangent line. The proof of the mean value theorem is a little bit more complicated than I'd like to get into at this point. But a good interpretation of the mean value theorem is given here. If we imagine taking 2 hours to drive to a town that's 100 miles away, then our average speed is going to be 100 miles divided by the 2 hours, or 50 miles per hour. Now remember, our instantaneous speed is almost certainly not always going to be 50 miles per hour. But the mean value theorem says that at some point during that trip, instantaneous speed has to equal average speed. In other words, in order to average 50 miles per hour, there has to be at least one point on the trip where you're going 50 miles per hour. So let's take a look at example 2, the mean value theorem in action. The lapse rate is the rate at which the temperature T decreases in the atmosphere with respect to increasing altitude Z. It is typically reported in units of degrees Celsius divided by kilometers, and is defined by gamma equals negative dt over dz. When the lapse rate rises above 7 degrees Celsius per kilometer in a certain layer of the atmosphere, it indicates favorable conditions for thunderstorm and tornado formation, provided other atmospheric conditions are also present. Suppose the temperature at Z equals 2.9 kilometers is T equals 7.6 degrees Celsius, and the temperature at Z equals 5.6 kilometers is T equals negative 14.3 degrees Celsius. Assume also that the temperature function is continuous and differentiable at all altitudes of interest. What can a meteorologist conclude from these data? Now the figure shown here shows the two data points plotted on the graph of altitude and temperature. So here we have The first point, 2.9 kilometers at 7.6 degrees Celsius. And here we have 5.6 kilometers at negative 14.3 degrees Celsius. Now we can find the slope of the line joining these points using the slope formula that we've known for some time. So we take the change in y over the change in x, and we calculate that, and here we see that it's negative 8.1 degrees Celsius per kilometer, which means that on average the temperature is decreasing at 8.1 degrees Celsius per kilometer in the layer of air between 2.9 kilometers and 5.6 kilometers. Now, only having these two data points, we have no idea what the entire temperature profile looks like. So here the dotted line is just indicating that something is going on. Now, the mean value theorem guarantees, though, that there has to be at least one altitude at which dt over dz is negative 8.1 degrees Celsius per kilometer. At each such altitude, the lapse rate is gamma equals negative dt over dz, which is 8.1 degrees Celsius per kilometer. And because this lapse rate is above the 7 degrees Celsius per kilometer threshold associated with unstable weather, meteorologists might expect an increased likelihood of severe storms. Example 3 asks us to verify the mean value theorem. And it says, determine whether the function 2x to the third minus 3x squared plus 1 satisfies the conditions of the mean value theorem on the interval from negative 2 to positive 2. If so, find the points guaranteed to exist by the theorem. So because this is a polynomial, it's continuous and differentiable everywhere, so it satisfies the conditions of the mean value theorem. The average rate of change of the function on the interval is given by the slope of the secant line. So we take f of 2 minus f of negative 2 over 2 minus negative 2, and we have 20 over 4, which is 5. So the slope of the secant line in this case is positive 5. The goal is to find points in the interval from negative 2 to 2 at which the line tangent to the curve has a slope of 5. In other words, we're trying to find the points at which the derivative is 5. So taking the derivative here, we get 6x squared minus 3. Setting that function, the derivative function, equal to 5 gives us x squared equals 4/3. So the points that are guaranteed to exist by the mean value theorem are positive and negative 1.15, approximately. So you can see here's a picture of the secant line connecting from negative 2 to positive 2. And here are the points at negative 1.15 with a slope of 5 also, and positive 1.15, which also has a tangent line with a slope of 5. In addition to that, the mean value theorem has 3 consequences of interest. Now, I've told you previously that the derivative of a constant function is always 0. In other words, if f of x is c, then f prime of x will be 0. Now that we've discussed the mean value theorem, I can tell you that the converse is also true. If f is differentiable and the derivative is 0 at all points of an interval, then the function must be a constant function on that interval. And we can look at the proofs the next time we meet if you're interested. Our second consequence of the mean value theorem states that if two functions have the property that their derivatives are equal for all x on the interval I, then f of x minus g of x equals c on I, where c is a constant. In other words, the two functions differ by a constant. And our final consequence, suppose the function is continuous on an interval and differentiable at all interior points of some interval. If the derivative is greater than 0 at all interior points, then f is increasing on that interval. If f prime of x is less than 0 at all interior points of I, then f is decreasing on I. Now this is actually a portion of the first derivative test. Now that we have the mean value theorem, we can actually prove it. That concludes this video lecture on the mean value theorem.